Okay, so today we're going to be looking at section 9.8, and this is on the Maclaurin and Taylor, and then the difference now is that we're looking at series. Okay, series. So power series encompasses both Maclaurin and Taylor. Okay, so if you think of it, think of like you're either a boy or a girl, but we're all human beings. So Maclaurin would be like one gender, Taylor would be like the other gender, and then power is encompassing everything. So power series is just a general name for both the Maclaurin and the Taylor. So we defined Maclaurin and Taylor polynomials with a finite last term, namely n. In this section, we will extend the notation for Maclaurin and Taylor polynomials by going to infinity. Since the upper index is now infinity, we call these Maclaurin and Taylor series. So we're just switching the word from Maclaurin and Taylor polynomial to Maclaurin and Taylor series. Okay, so if you look at the two definitions, I'm just going to highlight the differences on this one. So here you have Taylor series, and the reason is that it is not centered at 0. So it's centered at x sub 0, so it could be any number other than 0, and so that's what makes it as a Taylor. And then the difference here is, instead of having the upper limit on your sigma notation to be n, it's going to be infinity. And can you tell me what other differences that you see from this listing? Read through all this, and what else is different from what we had as a polynomial?
It's the x.
Well, the x is, yeah, I have the infinity here. Look at the very end, guys.
Just have an n.
Yeah, so it's just this part right here.
So n.
There's no end, because it goes out to infinity. Whereas in the Taylor polynomial, we stopped it right here. Okay, so that's really the only difference. And so then if you look at this one right here, for the Maclaurin case, we have that it's centered at 0. So see, these are all 0, 0. And then the difference now is that we have infinity up here and plus dot, dot, dot. Okay, so even though it's a kind of a small thing, when you are doing these problems and you want to represent a series, you have to put that plus dot, 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 or else you'll be referencing a polynomial versus a series. Okay, so for time purpose, this example number 1 and 2 is just getting you to practice writing out all the stuff that you had from last night, except you're going to make it as a series. So I'm actually going to skip over this, and if we end up having time at the end of the period, we'll come back to it, but I want to get to the meat of the lesson, which is the next page. And so example 1, okay, skip over that, and then again with this one, it's going to be the same thing. You're just extending it with a polynomial versus a series. So the main part today is this radius and interval of convergence. Okay, so to introduce this, I want you to take out your calculator, and we're going to look at a certain graph. All right, so if we could just clear up the calculator, and so everybody has the exact same setting. So just do second plus 712. And just clear it up. And I'm going to use the series that has 1 over 1 minus x. Okay, so put in 1 divided by parentheses 1 minus x. Okay, so the expansion of this is your basic geometric series, which is 1 plus x squared plus x to the third, and so on. And so on the second, well, first of all, go back to window, and let's just change it from negative 5 to 5 for everything. Negative 5 to 5, negative 5 to 5. Okay, so we just want a smaller window on that. Now put graph on. And so this is the graph that we want to try to replicate. So 1 over 1 minus x is not a polynomial. All right, so the whole point of what we did in the last class is to say that because polynomials are so friendly, right? Aren't they friendly? Easy to take derivatives, easy to take integrals. They just look really nice. Whereas this rational function is not very friendly. We're going to try to make an equation that's a polynomial that will fit this. Okay, so let's just take it term by term. So the first term will say 1, put in 1, and then backtrack and make this a fat equation. Right, so just go back to that slant part there, the slope part, and just press that. All right, so this is my first term, and now I'm going to press enter. And so this is not a really good representation of what the graph is, because it's only intersecting at that one single point. Okay, so now let's add on another term. So this sequence, what it states, the series states is that now I can add on x. Okay, now let me just go back to where I'm getting all of this. If you recall back on, you don't need to turn it, I'm just going to show you where this thing came from. We went through and we actually did this problem in our last class session. So see, this is your 1 over 1 minus x, and then we tried to show that that is exactly this. So this is what I'm trying to put into the calculator. Okay, so that's actually the polynomial. All right, so now graph it, and we're going to look at the way that it behaves. It's a little bit better, right? So we're comparing the dark graph to the thin graph, and we're trying to see, can we get it so that it'll match up a little bit better? All right, so now let's add on another term. So then let's say plus x squared. How is it? It's getting a little better, right? So now in this particular region, before it was just 1 point, and then it was just kind of a line, but now we can see in this region it's overlapping. So when I say, is it a good equation or a polynomial, I'm asking, is it overlapping as best as it can? All right, so it's getting better now. All right, now let's do another one. So I'm going to now add on, what would my next one be? X to the third power. So then we have, how is it? Getting better. And let's do another one. Plus x raised to the fourth power. How is it? Pretty good. Okay, now I'd like you to try to add more terms. I'm going term by term. Why don't you add on the next 2 terms, and then add on the next 3 terms. And I'd like you to see, I'm going to stay by my microphone here. I want you to see how many terms you can add on so that you will get a better approximation of that particular graph. Right? So you're just going to go through and keep adding on terms. I'm going to now pause the video. Okay, so I have one person's, which is, oh, yours is still graphing. Okay, so I'm going to take a look at this. So then this right here is, what power did you say, Emily? 15. So she went up to the 15th power, and just look at the amount of graph that it's overlapping. So it's like right here to right about here. Okay, and then we have Brooks, which is about like this. Oh, it's still going. Yeah, it's still going. Okay, so do you see that even up to the 17th power, did you get yours to graph, Brandon? Yeah. All right, so can I see yours for just a second? The 20th? Okay, so here's the 20th. And do you see that the 20th versus, I think I had the 4th? It's not that much better, is it? I mean, look at, it's just like up to here. I'm just pointing it to here to here. And then I have this region. So there is actually a limit as to how well you can fit a polynomial. And that's what today's topic is about. And that is called the interval of convergence. So even if Brendan were to sit there and put in up to the 100th power, which I recommend that you don't do because you're wasting your time. So you will not get any better than what is stated. Okay. Okay, so then with that, let's take a look at these, a few terms on here. So we're looking at something called the radius and the interval of convergence. So for radius, I'm just going to abbreviate it as R, and then for the interval of convergence, I'll say IOC. Okay, and then this is the theorem. For any power series, so power series includes the Maclaurin along with the Taylor series, exactly one of the following is going to be true. All right, so the first case is the series converges for only that one single point. So this is actually a bad case. So I'm going to say bad case. Hello, whose happy day is this? Who? Juan? JJ? Juan. Happy day. Okay. So that means that it's only good for one point, which is really not even that good. And then the second case is the series converges absolutely, hence converges for all real values of x. So a case like this would be during the first lesson when I had you guys start off with a sine graph, and then we kept extending it, and then it got better and better continually, right? So this is very good. Oh, can you move that string? So like, or just move this. Okay. Wait, what am I doing? Okay. All right, and then the third scenario that we have is that the series is going to converge, but it will be for some finite interval in some parts on this. So you're going to have your center at 0, and then it's either going to go out like maybe 1 unit to the right and 1 unit to the left. So there are actually 4 scenarios for this, 4 cases. Okay, so I'm going to use the negative r to r. So it could be that the endpoints are not included. So it might be negative r to r, parentheses. Another case could be it includes that first interval, or the first part here, and so that will be bracket negative r to r. So it includes the one endpoint but not the other. And then the third case could be it doesn't include the negative r, but it does include the r. You could probably guess the last one. What's the last case? Both. Okay, so as you can see, this requires the most amount of work, this third scenario. If you get this one and this one, you're pretty much done after you do the initial part of the problem. Here, you have to check the one endpoint and also the other endpoint. Okay, so I'm going to now state all of this in words. So this theorem states that the convergent set for a power series in X is always an interval centered at 0, because it's a Maclaurin. For this reason, the convergent set of a power series is said to X is called the interval of convergence. In the case where the convergent set is a single value at x is equal to 0, we say that the series has a radius of convergence of just 0, which is not very interesting at all because it's just that one single number. In the case where the convergent set is from a negative infinity to infinity, the series has a radius of convergence of infinity, best case scenario. And then in the case where the convergent set extends between a negative r to r, we say that the series has a radius of convergence of r. Okay, so this is kind of mediocre, right? So we have the worst case, the best case, and then the final one is kind of a medium case. So the one that we just went over is a medium case, because it went from a negative 1 to 1. You know what, I think this is kind of deceiving because I paused, and then it still kept going. So I think I'm going to go up to about 17 on this one. But thank you for reminding me. Okay, so in graphical form, this is what's going on. So if the radius of convergence is just at 0, the radius of convergence is equal to 0, I'm going to use green for converging and pink for diverging. It's only good at one single point, and it's bad everywhere else. And when I say bad, it just means that it's diverging and it's kind of spinning and doing whatever it wants. It's not a very obedient type of graph in those regions. Okay, so the second scenario is the best case scenario where the radius of convergence is infinity, which means that it is good everywhere. Good, good, good. Very obedient. Complies to everything on the graph. Okay, that's how children should be. Children should be obedient in everything. Okay, not just at home, but at school, everywhere. Now you get, I'm going to call this a teenager case. Okay, so what are teenagers? They are complying in some region, right, like this. So maybe you comply at school, and you're a little bit disobedient at home, diverging here. That could be the other way around. Give your teachers a headache, though. Okay, so that would be the case where it is, radius of convergence is going to be r. Okay, so that graphically is what is going on, and our task is to determine, is it the first case, is it the second, or is it the third case? Okay. Okay, I'm going to stop my recording now.